started. Okay, so I want to conclude with a final remark, which is about kind of I mentioned it already because it was asked, but this idea of the self-shrinkers with least entropy. Okay, or in other words, this is related to the best constant in the Ricci regularity theorem. Okay. Okay, so the first, as I mentioned, just by very trivially, you can see that the entropy of any hypersurface, again, I mentioned this is bigger than 1, so of course this implies that the flat plane has the absolute minimum. Right. And similarly, as I mentioned already, right, if the Brocchi's theorem, basically the Brocchi implies that there's some epsilon depending only on dimension, so that the entropy of gamma, which is non-flat, let's say gamma is not Rn and a shrinker. Right, so remember this is, of course, as I mentioned, this is F gamma. This is bigger than or equal to 1 plus epsilon. Okay, so we know that this is the absolute minimum, and there's a gap to the next possible one. So then the question is, well, can we characterize this gap? So the question is, the question here is, can we Okay, and so the point is it should be reasonable to expect that somehow, we're looking for the minimum of some functional, it should sort of be stable in some sense. So it's not implausible to assume that it's, that the gamma that minimizes which would imply, of course, that gamma was, again, not exactly, but this is the idea, is that maybe it should be one of these cylinders, and then one can compute that at the entropy of the cylinders, this was actually computed by Stone, that this is actually achieved, the smallest value is actually achieved on the round circle. So he computed the Gaussian surface areas, but it's the same as the entropy, as we saw already. Okay, so that would suggest that the minimum is the round sphere. Okay, but the problem is, of course, this isn't really, we can't there's no way that I know to kind of formalize this, because right, we're not minimizing. The point is the entropy is a kind of min-max phenomena, so we're not really minimizing the entropy. We're among surfaces where we would be minimizing among self-shrinkers, and if we wanted to look at it in terms of all hypersurfaces, it would be as a min-max type of critical point. So it would be much more involved in making this work. So this, in this generality, we might conjecture that this is the minimum, and so far that hasn't been proved. However, we have the following theorem, which is a special case of the theorem I mentioned before, but is easier to prove. So I'm going to prove this theorem. This was due to Kolding, Ilmanen, Minicozzi, and White. So they said that if gamma is a closed self-shrinker, then the entropy of gamma is actually at least that of the ground sphere. Okay, so here, remember, this is the same as, in other words, f of gamma. Okay, so here we're making this pretty strong assumption that it's closed, right? Which of course doesn't answer the full question, because it's possible there are non-closed ones which are not flat but have less entropy. So this is again this we generalized. I mentioned before. This can be, as I mentioned, we can generalize this to actually any closed type of surface. Okay, so that's one thing that's true. The other thing that is more involved, and this is due to myself and Wang. So we can't answer this question completely in dimension 2. So when if gamma a non-flat So in fact, in dimension 2, we have actually the optimal value for this Brocchi regularity theorem, and it's achieved by the value of the round sphere. And in fact, we can prove a little bit more. I think I mentioned this, but I'll repeat. So in fact, if you're a self-shrinker and your entropy is below that of the cylinder, then you have to be either the cylinder, the sphere, or the flat plane in dimension 2. So we actually have a complete classification of these sort of low entropy guys.
So if you assume, say, if you know this is convex, then do you know it must be compact, like shrinker?
The shrinker is convex.
If you know it is convex, then...
like strictly convex? Or
yeah, strictly convex. We do know that.
Then it should be compact, yeah. At least in codimension 1.
Exactly. Okay. But mean convex would not imply...
Would not imply what? Compact?
Yeah.
No, so there's a cylinder. I mean, then it would have to be a cylinder.
Oh, okay.
Yeah. Yeah, so it's mean convex it is true, but so the point is we're not making any assumptions on the curvature. Okay. All right, so this is completely answers the case in dimension 2, but this is, and the proof of this uses ideas similar to the proof. I'm going to present a proof of this first fact by Colding and Minicozzi and White. We use ideas of this, but at some points, and I'll mention it, the fact that it's closed, the important point we're going to use for closed is that if you have a closed initial hypersurface for a mean curvature flow, it forms a singularity. Obviously, that's not necessarily true if it's not closed, and that's really the cause of why this argument is harder, and we have to do more work. And in fact, this proof uses Brendel's result, which is, as I mentioned, why that's really the reason it's a two-dimensional result and not a higher dimensional result at the moment. Okay, so that's this results for these low entropy shrinkers. And as I said, even though, I mean, this seems to be kind of like as I mentioned, there's a kind of variational aspect to it. We're going to actually prove this using the mean curvature flow, so it's going to be a parabolic proof. Yep.
Is that lambda always finite, or it might be infinite?
For a self-shrinker? For a self-shrinker, if it's proper, then it's always finite. So, I mean, you could obviously, a non-proper surface, it would be infinite, potentially. But, and of course, there's a question, is can you have a non-proper embedded shrinker? But I believe that's highly unlikely. So yeah, so this, in general, it's finite. But of course, if it's infinite, then it's trivial. So, okay, so we're going to try and prove this theorem. Right, so how is it going to go? So we're going to consider, let me sort of outline the proof, and then I'll fill in the details. Okay, so there's basically 5 steps. So the first step is we're just going to consider a gamma that's not the round sphere. So we want to the goal is to prove the entropy of this is bigger than the entropy of the sphere. And we're going to observe, in the second step, we're going to check that we can perturb gamma so that the entropy, let's call it to some gamma prime, so that the entropy of gamma prime is strictly less than the entropy of gamma, and that gamma prime has a certain convexity property. Okay, so the fact that you can decrease the entropy just has to do with the fact that gamma not being a sphere means it's entropy unstable. So that's not hard to see. This convexity property will also be fairly easy. It has to do with the fact that, when I mean convexity, I mean it's something like mean convexity, but not exactly the same. So it's we'll see it when I get to this step. Right. So then the third step is to consider the mean curvature flow, say sigma t, with initial data, this perturbed surface. Right. And the point is, what we're going to show, and we're going to show that this convexity property is preserved. Okay. So it's, for example, it's a known fact that if it's mean convex, then that's preserved under the flow. So this convexity property that's like mean convexity will also be preserved. And so then we know that it's preserved along the flow. And then the fourth step is to see that, you observe that, of course, t, the final time, is less than infinity because we're starting with the closed initial data as the right. And then the point is that there's the singularity model. This convexity property is actually the convexity of the flow. Implies the singularity model is mean convex. Okay, so this convexity, when you has a certain, it's not itself mean convexity, but when you blow up, you get mean convexity. And then the point is, of course, then we know. So let's say the singularity model is. Let's call this. I don't know. Running out of capital Greek letters. Theta. So then the point is. The point is the entropy of gamma is then, of course, strictly bigger than the entropy of gamma prime, which is then greater than or equal to the entropy of theta, the singularity model. But of course, the entropy of theta is, because it's mean convex, is square root of 2k sk plus r to the n minus k. So this is, of course, bigger than or equal to the entropy of the sphere. Right. Probably what we observed before. So that's the idea of the proof. This is step 5. Okay, so really the heart of the proof is in really it's these three steps. These first and fifth are kind of obvious. Okay, so let's say some details. So let's look at the proof. So let's look at step 2 more carefully. So the point is we know that since gamma is not equal to the round sphere, this implies that gamma is not mean convex. Right. Which in particular implies that, H gamma is not the lowest eigenfunction. Because if it was the lowest eigenfunction, it would have to be have a sign. Right, so that in other words, if you look at the lowest eigenfunction, lambda 1 of minus the linearized operator, that's actually less than minus 1. Okay, so now if we pick u to be the lowest eigenfunction, or the associated eigenvalue, the associated eigenfunction to lambda 1, right, we can normalize, so let's say u is positive. Since it's the lowest eigenfunction, it doesn't change sign. And let's maybe just make the CQ norm equal to 1, so it's non-trivial. So we have this lowest eigenfunction, and we can just deform gamma t by taking the normal graph. So this is going to be the normal variations, right? So we have our gamma, and this would be t positive is something like this. This is okay. And the point is, because u is orthogonal to the mean curvature and also obviously orthogonal to the translations, we can see that at least for t very small, that the entropy of gamma t is strictly less than the entropy of gamma. And t is small but non-zero. So if we do a deformation, we are decreasing the entropy. And the other thing we can observe is that, and this is this L gamma, it turns out, is the linearization of the shrinker equation. This is not too hard to tell. So if you look at the derivative at t equals 0 of the, I think it's the one I went to, minus h. Right. So if you compute sort of this sort of shrinker equation of these perturbations and differentiate it to equal 0, that's sort of the linearization of this shrinker equation. You'll see that that's actually L gamma of u. Okay, which of course is equal to minus lambda 1 u, which of course is strictly bigger than u, so it's positive. Okay, so in other words, these guys, as we go out, have some positivity for this curvature type term, which of course, if you think about it, this sort of almost looks like a mean convex in a certain sense, but we have this star-shaped type term. It's kind of like an interpolation between star-shaped and mean convex. Okay, so the point is, this implies, of course, that again for t small and positive, well, let's say t small and now positive, we can make the minus h gamma t. We can make this strictly positive. Okay. Okay. So the point is now we just pick gamma prime, so that both let's call this star and okay, so this is our condition, is that this is positive. Okay, so this is our convexity condition, that this quantity is positive. Okay, so now the point is we want to start the flow. So now we're into step 3. Okay, so now we start the flow with. Right, so we get this. mean curvature flow okay, right, and we know the initial data has this entropy bound, which obviously is preserved, and then also we have this positivity. So the question is, what is the quantity that gets preserved? And actually, let me just slightly change this. So I want to let me. Sorry, I should have checked my notes. So actually, I want to start the flow from time -1, just it makes notation easier. Okay, so my initial time is at -1, and it's equal to gamma prime, and I run the flow. And so what we observe is that we're going to introduce a quantity S. So we define on the flow the function S, which is defined to be 2 times the time times the mean curvature of sigma t plus x dot n of sigma t. So the position vector dot n of sigma t. So this is as I said, this is sort of, I mean, it depends on the different times. So, but notice at time -1. So notice on sigma -1, we have that S is positive. Okay, that's our assumption right here. Okay, so now the point is we want to claim that this is actually remains positive along the flow. Okay, so the claim is that this actually remains positive along the flow, and the way to see this is this following computation, which again is not hard, and this was originally considered by, I guess, Moychek. Can't spell his name. C-Z-Y-K. So if you look at the evolution of this scalar S, then that's given by the right. So if you know how anything about mean curvature flow, you know that the mean curvature satisfies this equation. So it turns out even if you multiply by the time and include this term, then this also satisfies this equation. But the point is, this is of course such a good sign for the maximum principle. So by and everything's compact, so you don't even have to do any it's just the standard maximum principle, standard parabolic maximum principle implies that the min over sigma t of S is bigger than or equal to the min over sigma -1 of S, which of course is positive. So we get that this S remains positive along the flow. Everyone should be, I mean, again, this is the idea that mean convexity is preserved. This is sort of a special case of this. Okay, so then we're in step 3. And so now we want to finally, now we want to get to step 4, which we want to show that somehow this mean convexity property is good enough to allow us to say something about the tangent or singularity models. And of course, again, going back to this theorem, let me just say, the only place we used we're going to have, in the end, the only place we'll have used closed is really in an essential way is to prove that there is a singularity at all. So if it's not closed, then there may be no singularity, and we don't know how to handle that in general. But in dimension 2, we were able to deal with that, but in a higher dimensions, we don't know how to deal with that. Okay, so what is step 4? Okay, so again, we're going to see something that we saw previously and also in other talks. So we're going to on this flow, we're going to consider a certain ratio, R, which is the ratio in the second fundamental form squared of sigma t divided by this quantity s squared, right? So again, s is positive, so this is well defined. And again, if you do some computations of this quotient, you'll see that it satisfies the following differential inequality. Okay. Which again is allows us to apply the maximum principle, though of course now the sign is reversed. So again, by the parabolic maximum principle, implies that basically the soup, or the max, I guess I should say, because it's closed, the max over sigma t of this ratio quotient r is less than the max of sigma minus 1, of r, which is just some finite number, right? So we just call this, so it depends on the choice, but it's finite. So in other words, we see that this implies that the second fundamental form of sigma t squared is less than or equal to c times s squared. Okay. Or in other words, right, so this is equal to, right, so in other words, this is equal to c times 2t, the mean curvature of sigma t plus x dot and sigma t squared. Okay? Okay. And in fact, I mean, you have to think about this a little bit. I mean, among other things, this tells us, but I mean, it's a little bit, you have to be a little careful. I mean, going back to, I should have mentioned this, right? I mean, strictly speaking, one needs to prove this, but maybe you can take this on faith. Of course, the fact that s is positive means that for the mean curvature to blow up, you have to have t being bigger than 0. So, you know, we haven't. You can either. It's now known, but you can prove it a little more directly. And you should observe that if t is bigger than 0, so the singular time has to be past 0, because we know the mean curvature has to blow up at the singular time, which of course is this result that's been recently proved, but in fact it's simpler in this setting if you do it a little more carefully. Okay, so this tells us that the point about this is, of course, as we get to a singularity, I mean, this quantity is always bounded because it's just a position vector dot normal, and it's always contained inside of a ball. So, and we know the curvature has to blow up as you get to a singular time, and we know t is positive, so that kind of forces the mean curvature to also blow up in order to have the inequality, right? So what this essentially says is that at the singularity model has to be mean convex. It's a little more complicated in principle. So let me just say what happens. Right, so the idea is, if we let, say, I guess I wanted to call it Vt, be the, say, tangent flow, be a tangent flow, at the singular point. Right. We can see just by rescaling, right, that basically, again, there's some regularity issues which turn out to not be important, but essentially we think about how things dilate. Of course, this thing blows up, we dilate it, and this basically scales at the same rate. But this guy goes to 0 because he's not, he's not. When you he's bounded. So if you dilate, you're making these bigger numbers get smaller. So this guy gets dominated. You end up with the estimate. Okay. Right. So again, the point is this implies that essentially either, V minus is mean convex because there's some points where the second fundamental form is strictly positive, or somehow the V minus is flat. And what this could mean is that, for example, it can't be flat multiplicity 1 plane because it's a singular point, but it could be a high multiplicity plane. Or a flat cone. Okay, so either it's mean convex or it's flat, right? So that's the only. So in this case, of course, this implies that right, which of course is that, as I already mentioned in step 5, we're good. So this part is okay. The point here is that we finally, and I didn't mention this, but of course we know that in fact the entropy of the sphere is actually strictly less than 2. So you can't have a double plane because that would have entropy above. You could have a double plane, but then you have proved the theorem anyway. And then the flat cone, of course, a flat cone is just there's one. That would be something like two planes that intersect at some angle, for instance. Right, that would be an example. But of course, that also has density at most 2. So you also have the theorem in that case. There's one annoying situation which has to do with the following fact, which is that so this theorem weirdly, well, I guess it doesn't happen in this case. So there's actually one annoying cone which sometimes you have to worry about in these things, which is that you take a sort of triple junction. So that's also a flat cone in principle. So this would have entropy. This would have entropy 3/2. So the entropy of this guy is. But it turns out that 3/2 is actually also bigger than the entropy of spheres when n is bigger than or equal to 2. Okay, so S1 actually this is actually less than. So in one-dimensional case, this argument, in principle, you'd have to worry about this, but that doesn't happen. And in fact, there's you never actually have to worry about this because there's a very interesting result of Brian White that says this is notice that this can never have the structure of a mod 2 flat chain without boundary because it always has to have boundary because just the way things count. And you can prove that any of the rescalings always has to be closed or be closed with respect to the have no boundary in some sense. So this would never arise as the limit of a smooth flow. Okay, so that basically proves the result. So if you're mean convex, you're good. If you're flat, you're also good. And so then you've proved the result. Okay, so I don't know. I don't really have. I didn't. This went faster than I thought. So maybe I'll just stop here.
so this content link looks like very similar to what Hussein did in the earlier, when he analyzed say the singularity of the mean curve, right? He also used similar result. Except here you have this F bar curve, right?
Yeah. So I mean,
right? So this, so this is like a small computation. So that is kind of estimate.
yeah. So I mean, he was interested in, So I mean, maybe I should remark, the interesting thing about this estimate is, of course, at t equals 0, it tells you that it's star-shaped. Right, that this is x dot n positive. So Smoychik was actually, I think, interested in. He looked at star-shaped, yeah. So you could also just use this concept, and if it's star-shaped, then this is the quantity that remains positive in the future evolution of the flow. Yeah. So I mean, this is somehow, it's sort of star-shaped is not preserved, but star-shaped plus this mean curvature term is preserved. So the point is, we start at at -1, where it's sort of measuring some kind of mean convexity for the shrinker mean curvature in some sense. Yeah. So I mean, I should say, maybe I'll just say in words, what happens in non-compact. So it turns out in non-compact, almost everything kind of goes through. You just have to do more work because all these maximum principles are on a non-compact manifold, so you have to do more work to make them hold, but they do hold. But the problem is, as I said, you fundamentally just don't know that it's become singular at any time, so you can't do this part. So this is the one part that doesn't go through. But what you observe is that, of course, at time 0, you see that you actually are star-shaped, right? So the point is, either you become singular and your analysis goes through and you have the entropy lower bound, or you get up to time 0 and you're star-shaped. But of course, being star-shaped in, say, if you're a surface in 3 dimensions and you're non-compact, it means you're topologically the plane, right? So then you can just use Brendel's result because you know that your original shrinker had to be a plane, but then it had to be flat. So there's nothing to prove in some sense, right? So that's how you work in dimension 3. The problem is in higher dimensions, you still get this sort of star-shapedness assumption under some reasonable assumptions on the shrinker. But of course, there may be star-shaped. There may be sort of topologically trivial shrinkers that are not flat. That's really, you don't know in higher dimensions. So that's where the argument breaks down. But yeah, definitely this part is, I think, been understood. Maybe not with this function, but I think the important part is that it, you can use this to force your singularity models to look nice, and then you can use that to tell you something about the entropy. Right. So, this result is, and I should say, I think this argument was actually inspired by work of Ilmanen and White, who looked at the lower bound of the density of certain area minimizing cones. So it's a similar idea where you sort of force the flow to become singular, and then use that fact that it becomes singular to, singular and a singular of a certain, curvature type. So then you know what the singularities look like, and you can go backwards and get something about the density of the original cone.